Okay, welcome back, guys. We are going to be doing tutorial 2, unit 2 on physics 2, so that we can make sure that we simplify the concept. So let's begin, guys. Okay, this is a wire, right? What you need to understand is that when current starts going into the wire, there will be magnetic field that will develop around the wire, which means the magnetic field will begin moving is when current starts moving inside the wire. So when the current starts going up there will be magnetic fields that will be produced. So to find the direction of the magnetic field, we are going to use the right-hand rule. We call that the right-hand rule. Make sure that when you are doing this right-hand rule, you use your right hand, right? So now, do you see that the direction of the current is going up? So let's say this is your right hand, so your 4 fingers, and this is your thumb, and let's say this is your hand. So the direction of the thumb the direction of the current will be determined by the thumb, and the direction of the magnetic field will be determined by the hand, and the direction of the force will be on your at the palm of your hand. So this is the direction of the force at the palm of your hand. So now what you need to understand here is that, right, so let's say the current is going up there, right? The first thing that you're going to do, I'm going to use this marker as a pen, as my wire there. I know that the current is going well, it's going upwards, right? So I'm going to put my thumb in the direction of the what? Of the current, because the current is going up, my thumb must also go up. So these fingers, they're going to show me the direction of what? Of the magnetic field, right? Do you see that? The magnetic field, when I'm holding a pen like this, it will be like it's going in this direction, coming back like that, which means the direction of the magnetic field will be in this direction. So if you look at it, let's say you are looking at the wire like that. So there will be a circular around the wire. So which means, let's say this is my wire and my magnetic field will be appearing like this. So this magnetic field there, it will be appearing. So this is my wire. I'm looking at the top of the wire like this. It's like I'm showing you a wire like this. And then the current is moving in and you are seeing the direction of the what? Of the magnetic field. So from the wire, we treat as a center to the magnetic field. That distance from the wire to the magnetic field is called the radius. So the formula that you're going to use immediately when you see a wire, 2 wires or 1 wire, the formula that you're going to use for that is called, to determine the strength of the magnetic field, is called mu current all over 2 pi r. Remember, r represents the radius, right? Which is the distance from the wire to where the magnetic field is, depending on how big the magnetic field is going to be. Sometimes the magnetic field can even have bigger radius, depending on how strong the magnetic field is, right? And then we have the current, the amount of current that moves in here, whether 5 ampere, 50 ampere. So that is the current there. It is represented by I. And then mu, it is a constant, and that constant is 4 pi times 10 to the power negative 19, if I'm mistaken. Negative 7, sorry. Negative 7. So it's fixed. This one is always like that. It doesn't change. They will never give you anything. If they don't give you, if they didn't change it, it remains like this. But it is a constant that has to remain like that. So which means, in other words, let's say if the magnetic field is just 2 centimeters away. Remember, if something is given in centimeters, the radius must always be converted into meters. Make sure that it is converted into meters for you to be able to get the right answer. Now, looking at this formula, you can tell that if current increases, let's say for me to be able to increase the magnetic field, I have to increase the current. Because the current is at the numerator, so an increase in current will be an increase in magnetic field. But let's say, for an example, I want to decrease the magnetic field, which means I have to increase the denominator, because an increase on the denominator will decrease the size of the what? Of the magnetic field. So which means if I want to decrease the magnetic field, I have to make sure that I increase the radius. So the further you are from the what? From the magnet, the decrease, there will be a decrease in the magnetic field of the magnet. So which means the more you move away, the influence of the magnetic field to the metal or to anything that comes close to it becomes weaker and weaker. That's why when you increase the radius, or when you increase the distance of this thing, the influence that the magnetic field will have on that thing will also decrease. So this is the strength of the magnetic field. So every time when you see a wire, the first formula, don't use any formula. the formula that you are going to focus on when you see a wire that is being introduced, you must know that this is the only formula that can save you to get the right answer. All right, let me show you a concept where now we are given probably two wires that are parallel to each other. Remember, I've already introduced the formula for when you see a wire, you need to know that the formula that you're going to use immediately when you see wire, you must know that the formula that we're going to use is going to be magnetic field is equal to mu 0, which I explained that this one is equal to 4 pi times 10 to the power negative 7 all over multiplied by I divided by 2 pi r. Now, r, which is the radius in between this. Remember that current has direction, and the direction of the current influences what these two wires, the force between these two wires, which means when the current is going up and the current is also going up, remember, I'm going to show you something which you need to really understand. So let's say this is the wire here. I've already shown you that the direction of the current will be determined by the thumb. See that? So the direction of the magnetic field will be there. So current, which means magnetic field, will be entering in the page like this. So for entering into the page, use X, and then coming out of the page, use that, right? And then coming on the same thing again. So entering on the page will be X because it will be entering there, and your fingers will be coming out of the page in that direction, which is dot. So the dot represents out of the page. Remember that, out of the page. And for an X, it represents into the page. Okay, let's take this back to electrical so we can simplify this concept. Remember, electrical, when we have a battery, right? When we have a battery, let's say this is our battery, and this is a positive terminal of the battery, and that is a negative terminal of the battery. What did we say about current? We said current moves from the positive terminal and it goes back into the what? Into the negative terminal. You still remember that it's entering on the X, right? X means into the page, and then dot means out of the page, right? Do you see that this thing looks a bit like positive? Let's take it as our positive charge. And that dot, let's treat it as if it's our negative charge. Do you see also that X looks as if it's a positive? So let's take it as a positive charge. And then the other part, take it as what? As negative charge. Remember, a positive and negative charge, they have what we call a force of attraction in between them. Right? Do you see that? Which means these wires are going to experience a force, right? That is a force of attraction in between them. So now this is what we need to understand. So there is a force of attraction in between the wires who have the direction of the current going in the same direction. But let's say on the second case, there are still two wires here. And the current of this wire, let's say it's going down. And there is another wire again. And the current of this wire, let's treat it as if it's going where? It's going up. Now look at this. Do you see this one? The thumb is in the direction of the current, and then the curl finger still go there. So it enters through X and then it comes out through that. But look at this one. The direction of the current, where is it? It's going down. So I'm going to point my thumb down. But look at where my fingers are curling. Do you see? My fingers are curling in that direction, right? So when they're curling in that direction, which means they are entering through here and coming out through here. So, because that one looks as a positive, I make it a positive, and that one looks also like a positive, I make it a positive. These two looks like a negative. When a negative charge meets a negative charge, there will be a force of what? Of repulsion. So, which means these two will repel each other. So, which means when the current are going in different direction, there will be a force of repulsion that will be experienced by these two. So which means this will go in the other direction and this will go on the other direction. So this will make them to be what? To be like they are negative, right? And then this will be, when there's a force of attraction, there will be something like a positive in between them. So make sure that you understand that. This is the most important part that you need to get. So this one will be like a positive, right? When you are adding the total magnetic field because they are attracted to each other. And then here it will be a negative because they are repelling each other, right? So if they say they want the net magnetic field or the total magnetic field of this, look at that, because these are attracted, which means you're going to say B net, which is the net magnetic field, is equals to mu I, and then for this wire only is going to be what? 2 pi r plus y, because they are attracted to each other, right? And then you're going to say for the other wire again, Bi 2 pi r. It is only when they are repelling each other where you are going to put a negative. Alright guys, we are going to focus on 2.1, the question that is given to us. We are already given a wire and the direction of the current in the wire, which is shown that is going up. And then we have 2 points that are given to us, right? And then we have the 6 ampere current given to us. And here they told us that there is current that is moving in this wire. They didn't give us the direction, and they want us to calculate the direction of the wire. So they said the distance from here to here. They've already given us the distance. They said this distance is what? 0.5 d. Right. Let me use a different color there so that we can be able to spot it better. So the distance is 0.5 d. A distance from there to there. And they also mentioned something very important there. They said on point B, there will be the magnetic field there will be equals to 0 Tesla. What does that mean? Right. It tells us something. Which means the one thing you need to understand that for something to be 0, there must be a subtraction sign in between. So I can't say 5 plus 5 and expect to get a 0. I must put a negative sign in between, right? And then remember that okay, 5 minus 5 will give me equals to, for me to get a 0, I must put a subtraction sign in between. So at the outer point, that's where 0 Tesla is going to be found, which means also on the other point again, outer point, that's where we are only going to find our 0 Teslas, only on the outer part. So it's very important. So if there is the outer point has 0 Tesla and the outer point, this other point also will also have a 0 Tesla. Let's say maybe there's another distance again, which is called an O. From there to there, that's where we can only find our 0 Tesla. If they say to you the 0 Tesla is on the outer part of the wire, then which means on both outer parts of the wire, there are also 0 Teslas somewhere there. It's only on the inner part where there will be a positive. So if it is a negative, make sure that is going to be a positive in between. And I told you something. If there is a positive in between, what happens? That's a force of attraction, which means these things are attracting each other. So for them to be attracted to each other, what's the direction of the current? So the direction of the current will be what? Will be upwards. They are only attracted when they are going on the what? On the same direction. You get it? Right. So then this is how you answer number 1. So that's how you get it. So they've already told you that there is 0 Tesla there. Right? If there's 0 Tesla, the negative part, if they say 0 Tesla was on C, let me give you another example. If they said 0 Tesla was on C, for you to get 0, what are you going to do? You're going to put what? A negative in between. So that negative, which means 0 Tesla is only found in between these 2 charges, which means in any other point, which is on this part, there's going to be what? There's going to be magnetic field present and magnetic field present. So make sure that you understand that. So which means what is happening here, if there is a negative in between, that means they are what? They are repelling each other, which means the force of the direction here of these two, the force that will be experienced by these 2 wires will be a force of repulsion. And then remember that, and that's how it's going to be. So the direction will change if they are repelling each other. So this one will go at the opposite direction of this type of the wire. So remember that. That's what you need to get for the first part. So we've already answered the first question now. So we already know that the direction of the current there is going where? Is going up, right? And the force that is being experienced by this thing, it is the force of attraction. Definitely so, for them to be attracted, must be positive in between, because they told us that at point 0 there's 0 Tesla. So for me to get that 0, so I put a negative there and I put a negative there. So this is what I have now. So now I know that the direction of this current is in this part, right? It's going on the other part. So now, right, remember that for us to get the magnetic field as 0, right, the net magnetic field, which means the magnetic field of both wires at 0, it will be on this point, which means the radius from this wire must come right to the way the magnetic field is going to be 0. And the radius of the second wire must come from this point and come to this point. They've already given us that the magnetic field, the radius of this wire from this wire from the second wire to here, they've already given me that is 0.5 d. So here I already have the distance, and they said the distance from here to here is what? Is d, which means in other words it's d plus 0.5 d, and then which means it's going to be 1.5 d, which means from here to there is 1.5 d. But from here to here is 0.5 d. So let me call that I1, let me call that I2. So remember that, right? And then we are going to simply put it and try and subtract it, right? And see what's going on. So it is a net magnetic field, which is B net, equals to mu 0 I divided by 2 pi r minus, because I told you that they say the magnetic field is going to, for you to get a 0, you must subtract them. So which means I'm going to write for this is I1, I'm going to write for I2, mu 0 equals to what? I2 divided by 2 pi r. We already, remember that you already know that this is what? This is, they told you that the B net, the magnetic field, the net magnetic field is going to be 0. So I'm going to put my 0 here. It's going to be 4 pi times 10 to the power negative 11 multiplied by I1 divided by 2 pi. Remember, I1, do we have the radius for I1? Yes, we do. The radius for I1 is going to be what? 1.5. Then it's going to be 1.5. Remember, there's a d. Put a d there, right? And then I'm going to say minus. Same thing again. Let me just write it down here so we can all see it perfectly. 4 pi times 10 to the power negative 7. They gave me the I for this one, which is what? Which is equals to 6. I'm going to multiply it by 6 divided by what? By 2 pi. Do I have the R there? Yes, I do have the R. And they said my R is what? 0.5 d. Then I'm going to put my 0.5 d. So remember, this thing is more like this minus this equals to 0, right? So I'm going to take the negative one, which is this one, because there's a negative sign in there. Do you see that? Which continues to the other side. So I'm going to take this negative one and put it on the other side of the bracket so we can simplify it. So now, what is going to happen here? Let me just write it on top here so we can see it perfectly. Enough space. So it's going to be this one going to the other side, which is 4 pi times 10 to the power negative 7, 6 multiplied by 6 amperes, which is that current, divided by 2 pi. The R that we have there is going to be 0.5 d, equals to the other part, which is the first one there, which is 4 pi times 10 to the power negative 7 multiplied by I1, which is the one I'm actually looking for, divided by 2 pi 1.5 d. That's what I have right there. So remember, this will cancel with that one, right? And what else? 2 pi will also cancel with that one, and d will also come out, and then we are left with something like 6 all over 0.5 divided by I1 divided by 1.5. So when I simplify that to get my I will be equals to what? Will be equals to 18 amperes. Right. Now that we know that the next question, they say I must determine the magnitude and the direction of the magnetic field at point C. At point C here is in the middle, right? Remember I told you that there is a positive sign in between, which means now the magnetic field is not going to be 0 because we are adding. Remember, right? They told us that the magnetic field is 0, and they told us the point where it was 0, which was outside, which means it's going to be 0 there. It will not going to be 0 here. So it means it's 0 there, but it's going to be what? It's going to be a certain number. That's why I put a plus there. So now, which means now the new formula for B net will be equals to, B net is equals to mu O I1, because we already have I1, divided by 2 pi R plus, because there's an attraction in between, mu O I2 divided by 2 pi R. So now, how are we going to get our B net? So remember, this one is a constant, but you still remember it. So it's 4 pi times 10 to the power negative 7, which is clear. I have I1, remember that, Rene? Let me just write it here so that we'll plug it in a calculator when you're doing it there. So it's 4 pi times 10 to the power negative 7. Then it's going to be what? It's going to be I1, which is what? Which is equals to 18, right? Multiplied by 18, divided by 2 pi. Remember now, they told us about our R. They said our D, they changed the value of D. So they gave us now the new value of D, and they said the value of D is equals to 0.1 meters, right? And they told us that C is the midpoint of D, which means we need to divide this 0.1 by 2 because it's a midpoint. Midpoint simply means in between the two. So we divide it by 2 to get the real value. So which means a distance from here to here is 0.05. And the distance also from there to there, let me make it a bit bigger, 0.05. And also the same here, 0.05. So we have the two distances there, right? So which means here, when I come here, this wire right to point C, it's 0.05. And this, from this wire right to point C is also what? 0.05. Which means I'm going to plug in my 0.05 there. And then I'm going to say plus. Same thing here. Remember your mu is that constant there, which is 4 pi times 10 to the power negative 7. And then I have the current for the second wire, which is what? Which is times 6 divided by 2 pi. What is the value of the distance between here? Is still the same, 0.05. And then when I punch this in a calculator, right now, my new B net will be equals to what? 9.6 times 10 to the power negative 5. And this is how we get the answer.